All right. Okay. Hey, good morning, and thank you for being here for our Accelerated Discovery Lab Forum session. It is my real pleasure today to introduce Ira Schwartz from the Naval Research Laboratory. I've met Ira a long time ago, 8 years ago. Well, to me it seems like a long time ago. The first time we met, the day we met, he told me over a beer that the paper I'd worked on for my PhD was wrong, completely wrong. And we've been friends since. And, you know, he was probably right. You know. Ira got his PhD from the University of Maryland a long time ago. He told me not to tell when. A long time ago. And then after with Jim York, after a fellowship at the NIH, he moved to the Naval Research Lab, where he has been since. And is now the head of the Nonlinear Systems Dynamics section. Ira has contributed to a lot of fields, including mathematical biology for epidemiology, as we will see today, but also synchronization of coupled lasers and the theory of large fluctuations, first passage time for large fluctuations, and lately, as of late, on swarming. And so he has been awarded more than 10 meritorious citations from the Navy, one of them with a paper we worked together some time ago, and is fellow of the American Physical Society. Ira, thank you for being here.
Thank you very much for that kind introduction.
Well, it was kind because I didn't go into all the stories.
Right. So what I wanted to talk about today was avoidance behavior. If somebody is sick in the audience, right, and you knew about it, you wouldn't be sitting here. And so this prompted us to look at how social behavior actually changes when you're in a network situation, especially in the presence of disease or threat. Okay? And that's the theme I'm going to try to talk about today. And I have a lot of help. Laura Billings, who's at Montclair State currently, she's on loan to the NSF. Simone, who's the rock star employee, and one of several rock star employees. You know, Louise Pierre is with NIH. She's a part of our NIH project that we worked on. And Brandon Lindley and Eric Forgeston and Leah Shaw are all former postdocs at various institutions. And they contributed greatly. The network stuff is primarily by Brandon Lindley and Leah Shaw. That you'll see at the end. So, okay, disease is in the news constantly now. So this is even out of date. I think this only goes up to 2013. But you can see that there's a lot of stuff that keeps showing up sporadically almost, okay? Especially when measles hits Brooklyn, right? There's a, that's another country, as people remind me. And you see that the dengue experience keeps on, it's actually endemic in Thailand and Singapore. So it's interesting to see how many diseases are prevalent throughout the world, including Ebola, which actually is now to stay with us since the African outbreak. So you can see spatially just exactly what the situation is in terms of data for the diseases that hit at all these countries here. So you have measles out here that was recently, and then there's chikungunya, who's slowly moving up, and dengue is actually moving up into our country as well. And in Africa and even Australia, there's been recent measles outbreaks. So spatially it's broad. You might ask, well, why doesn't it ever die out? And you can even see how many outbreaks in time occur, right? So this is a recent paper, and so you can see in the upper left quadrant here that the number of outbreaks since 1980 is growing considerably over time, okay? And you can see some of the other breakdown here. The zoonoses versus the human-specific is interesting, and then, of course, you have various kinds of diseases, viruses, bacteria, and the like. But the important point I'm trying to make here is that the number of outbreaks that are being reported is growing, okay, as time goes on. So what we're really interested in knowing is what's happening when diseases do die out. And so the big problem is, do they die out on their own? When do they die out on their own? And how can we harness the idea of when they die out to make them, to add controls to make them die out faster? Okay? And so here's some examples where there's local disease extinction. So on this bottom panel here, I've plotted the infectives for dengue in one province out of 72 in Thailand, where you see bursts of the number of infectives that are separated by 0 numbers of cases, where locally you have die-out. Okay? And on the right panel here, it's the number of months with 0 cases as a function of population size. And you can sort of eyeball it, and you see that it's roughly exponential. And I'm going to make use of this in the theory, that the size of the population actually governs what kind of distribution you're going to be making an assumption about when you talk about die-out. So this is in Thailand.
So I'm trying to understand the number of months with 0 cases
That's right.
as a function of population size.
That's right. That's
so
what
the case, okay,
Okay?
okay.
So how does human behavior come into it? So if you look back at 1976, outbreak of Ebola in Africa, you find that it did die out, and they knew pretty much everything that was going on within the hospital where they were keeping the cases. And so they kept track of the routes of transmission, whether it's person to person, needle sharing, both, and the like. But the conclusion was that the reason it did die out and didn't continue was because people decided that, hey, it's not such a great idea to go visit people who have this disease in the hospital. Okay? And so eventually, even the corpses nobody would touch those. So the human behavior here is pretty much responsible for the epidemic outbreak that occurred back in '76. And we want to understand this kind of behavior and how it affects the transmission and the dynamics of a disease. And that's the goal of my program. So, as I said, we're looking at spontaneous natural disease extinction. How does a disease go extinct all by itself? Okay? And then we want to leverage that to try to look at modeling extinction and control to enhance it. That's the idea. Okay? So we want to quantify the effectiveness of the vaccination program, and we want to identify some sort of use of when you have finite resources. Okay? So you don't have enough to spend in terms of money, time, and, let's say, vaccination resources, but you want to be able to identify what the best way is to try to bring the system to the disease to extinction. Can I get a little bit more water? Thanks. Okay, so here's my agenda. So first I'll talk about stochastic adaptive networks. So how epidemics evolve on those, and then I'm going to incorporate human behavior on those. And then I'm going to talk about extinction and control in an adaptive network, and talk about the effect of vaccination on and enhancing that extinction project. And then I'm going to talk about analyzing fluctuations. So I'm going to go back and look at a very simple model when you have no network structure, but the population's well mixed. So I can show you the mathematical machinery and how to explain what's going on using a dynamical system framework in that particular aspect. Thank you very much. And then I'm going to try to extend that analysis to real networks. Okay, when you actually put the network into the case where you have an epidemic evolving on the network. Okay, so here we go. Okay, so first I want to talk about what do I mean about adaptive networks. So normally when you have real networks, there are random connections between nodes. You don't have any particular rewiring depending on the state of the system, but in an adaptive network, you do. Okay, so this is supposed to represent sort of use the mechanical one, the analog. You have a local dynamics where you're looking at a change in the state of the system, and that's going to feed into some particular change in the wiring of the nodes, okay, because of the state. And that will determine, again, what the local dynamics are going to do. Okay. In terms of rewiring here, I'll show a better picture of this later. If you have infectives versus susceptibles and you knew about it and you were susceptible, you would say, okay, I'm going to just break this link to the infective, so I'll reduce my chance of infection and rewire to another susceptible or non-infectious individual. And there are lots of examples of these adaptive networks. Okay, so where the adaptation occurs because the network actually changes as a function of the state of the system. Right? And so you have this feedback loop and that causes the adaptivity, and there are lots of examples of this. In fact, I didn't put the paper here, but there's a nice lobster example where they can actually sense the dens where disease occurs. And so they'll avoid that and go to some other den. There's some Nature paper. I don't have the reference here, I'm sorry, but it's a cool paper. Okay, so let me be a little bit more specific. So now I'm going to label things. So my nodes will be susceptible, infected, recovered, or susceptible again. And the dynamics are such that there's some probability of infection, so it's a rate of a susceptible becoming infective. And then there's recovery rate R. And then there's a resusceptibility rate. So I have an SIRS model here. And again, this is the picture of the rewiring where I have a non-infectious link to an infected individual, and because of knowledge of that, I'm going to rewire. Okay? And so we've done a lot of numerical work on this with 10,000 nodes and 100,000 links. And so these are the parameters. And what happens is that you can write down a very simple node equation describing a mean field of what the probability is of being in one of these states, susceptible, infective, or recovered. Okay. So it's a very simple model. It's just the stuff that's going in to the susceptibles from the resusceptible rate here, and then there's an infection that takes it out into the next compartment, and so forth. So it's a very simple nodal equation, but the problem is that you need to know what the links are doing. Okay, so it's a counting process. I'm not going to go into detail. I'll just show you what one link equation for the probability of having an SI link change, rate of change is. Okay? But I'm not going to say much about that, other than the fact that we do have a rewiring term here. But that's the basic idea. So I don't want to go into too much technical detail on that, and I want to talk about what kind of behavior you change when you turn on the rewiring rate. So without any rewiring here, if you plot the infectors versus the infection rate P, you always have just one endemic state, okay, where the mean field predicts steady state. Okay, and these black circles here are the Monte Carlo runs, and the theory is given by this solid line here. And then the extinct state here is unstable. So, you know, how does it go extinct? So I'll get to that in a minute. So as you turn on the rewiring rate, what happens is that you create a new state. You actually have bistable states here. Okay, so the extinct state here is stable for very low infection rates, becomes unstable, and then you see that there's an endemic state up here, but there's a region of infection rates where you have both extinct and endemic states coexisting. So just very small rewiring rates here cause a change in the dynamical behavior.
Is this
in the mean field
independent of the topology of the network?
Yes. No, it's not independent of the topology. So here we're just looking at random networks on it with an average degree of, let's say, 20. So if I pick a node at random and I look around at my contacts, they pretty much look the same for these runs we're talking about. Now you can I'll talk about the topology and the effects of it. Excuse me. So suppose I take a node at random, excuse me, and I look at the number of connections or the degree as a function of time. Just any random node in my network. Okay? And so it's color-coded here, where the green here are the recovereds, and the red are the infectors, okay, and the blue are the susceptibles. But you can see what happens here. So when you're recovered, right, you're going to some point in time where you'll start to be resusceptible. And then once you get infected, what happens? You start shedding nodes because people are avoiding you, right? There's some probability and some rate that people are going to be running away from you. And that's what these red curves are. And they do it rather rapidly. Okay? So you get this oscillation effect in the number of connections on average, okay, for any random node. And you can see that when you look at the distribution of the degree, okay, for the static network. So yes, so we look at a mean degree of about 20 in the static case. And then if we turn on the rewiring, which is what this represents here, then you see the distribution for the infectives is slammed down to something that's very small, right? Where the distribution of the susceptibles and the recovereds actually spread over a wide distribution of degree.
Are you conserving connections?
Yeah, well, conserving average degree.
Average.
Okay? In reality, that's not what happens, but it's a good approximation. So what you can ask for now is what kind of, as a function of rewiring rate and the infection rate, what kinds of dynamics you might see. So if you have very low rewiring rates, then you're always endemic. But if you increase the rewiring rate, you jump into a region where you have that bistable situation where the extinct state coexists with the endemic state. They're both stable. And then if you increase it even further, right, people are running away really fast, then you drive the disease to extinction, right? In that it's disease-free and it's stable, it's attractive. And then you also have some unstable oscillations here, and that's due to the effect that you have these degrees oscillations I showed you previously in this picture, right? So you get these oscillations here, and if you have stochastics on the system, then you can excite these large fluctuations. And we can characterize those fluctuations. Okay? So suppose I look at this particular node here, this point of the infection rate, where I have an unstable branch connected to this endemic branch that's stable. Right? Okay. And I look at the size of the fluctuations as I get close to this particular point. Well, if I plot the log of the standard deviation over the mean, so the relative size of these fluctuations as a function of that distance to that particular P0, that saddle node point, I get a great straight line here showing how the size of the fluctuations increase as they get closer. Okay? And so as the oscillations get bigger, there's a better chance for extinction. And so we'll define extinction in the following way. I'll look at the lifetime of a disease, right, as its time to extinction if I start near one of these endemic points here. So if I start here, I want to know what the lifetime is just before it hits 0 in the number of infectives. And so now if I plot the log of the lifetime versus p minus p0 to the 3/2, okay, I get this perfectly straight line here showing this very nice scaling law in terms of the distance away. So the log of the lifetime starts to drop down, so things get extinct faster because the size of the fluctuations is starting to increase as well. Okay, so we can actually prove this rigorously, this particular curve.
This is for fixed population.
Fixed population size. Yeah, it's closed, so there's no birth and death. Okay, so now I want to talk about extinction and control and the adaptive networks. Okay, so suppose now I want to know what happens if I couple a vaccination program along with this idea of rewiring. So again, I'll have S and I with an infection rate and recovery rate as before, but I'm going to introduce a new class. And I'm going to introduce a class of V that stands for vaccinated class. Okay, and I'm going to have a time-dependent vaccine program. And the vaccination program is going to be Poissonian. So there'll be an average frequency where I'm going to apply it. and I'm going to apply some fraction of that vaccine to a fraction A of susceptibles. Okay, so it's discrete vaccination. And again, I'm going to have the same kind of rewiring here, except for instead of S and R, I'm just going to have S and V. And I'm going to actually allow there to be a resusceptibility rate from the vaccinated class to the susceptible class. So it's a slightly different model, but not too, other than the fact that I've added a Poisson distributed noise, vaccination process here. So there's some interesting things that happen. So here's the node fraction on the upper plot and the average degree on the lower plot. In red are the infectives, okay? And these little crosses here along the split screen designate a realization of a Poisson process. Okay, and so these are the parameters here. And so you can see after a while, you don't see much of a change in the node fraction until all of a sudden you get this exponential drop that's very fast. But you look at the average degree here of the infectives and you see that, oh, there's a little bit of change. But now this degree of the susceptibles is going up rather rapidly here, okay, until eventually everybody sort of goes to zero, and then the susceptibles will relax. So what's happening is that as I go along, and I'm picking a fraction of susceptibles, the degree of the susceptibles is high. And so this actually agrees very nicely with a very early work by Vespignani and company, where they look at the vaccination of high degree nodes, and it provides better protection. They don't say exactly what better protection is, other than the fact that we can see very fast relaxation to extinction when you couple in the rewiring with the vaccination. You can see that better by actually plotting the lifetime in terms of the Monte Carlo steps. Okay, so in blue you have no rewiring in the network, and then in red you have the rewiring turned on. So the times here, so if I want to look at the amount of resource, so here I'm just adjusting the vaccination frequency, the times at which, how many times a year I'm going to be applying this. You can see that at the same time I require like over 2 orders of magnitude fewer applications in terms of the frequency.
Excuse me.
Yeah.
So I had a question about, so with your Poisson vaccination process,
Yes.
that leads to some natural clumping in the times you saw it on your previous diagram. I
Yeah.
noticed that the curve started falling. Yeah, there, the
Over
curve
here?
started falling, yeah, because
Yeah.
you had events sort of far apart, and then you had 2 vaccinations that came fairly close to each other.
Right.
And that was actually sort of where the part where the curve started to fall. Are those effects sort of an artifact of the Poisson modeling?
It's just one realization here. But we do this
Right.
lots of times to compute the Monte Carlo.
I'm just wondering if there is some sort of a clumping effect.
There's a natural clumping effect, and we've looked at that in terms of understanding why sometimes random vaccination programs with an average period do better than strictly periodic programs where you're right on the money, okay? So there's no variation in the application. And so essentially what happens is that, there's a relaxation time to go back to the endemic state. So I'm out of the endemic state, I bang it once. Now suppose there's a little bit of a longer lapse before the next pulse of vaccination, right? So before that time, depending on how fast it relaxes, I'm going to be going up, back to the endemic state. But now suppose I hit it once and then hit it again before that relaxation time occurs, so I'll drop it even further. So in a certain instance, right, you can show that the Poisson distribution will actually do better than strictly periodic vaccination because of that effect, right? So there's a probability that you're going to have, vaccination events that are faster than the relaxation period of the endemic state.
Yeah, because you can imagine sort of a gamma family of models, right, where you vary the shape parameter.
Yes, you can.
And the shape parameter of 1 gives you exponential Poisson, and you can get more or less clustering.
That's right. Yeah, absolutely. Yeah.
I'm sorry to pause for some basic questions.
Mhm.
Here, I mean, you're starting off in a state where almost everyone's sick. Is that, the red curve is at the top?
That's right. So we loaded this to sort of enhance this picture. So we loaded the infectives with the population as almost everybody is infected. That's right.
So when you do one vaccination, all of a sudden some people who only, I mean, in the initial state, everybody's surrounded by 6 people, so they can't rewire to spend their time visiting other non-sick people. But once you vaccinate people, you start to make it kind of kinetic.
Yeah, I understand.
It's possible to find people
You're
to
right.
rewire.
Yes, that's right. So the rewiring here is harder, right? So, you know, this, because we loaded this up to enhance this effect here, it's a little bit artificial. But that's why we plotted, you know, right, why you have such fewer susceptibles on average, right? The way you're looking around.
Right.
Okay. So, but you're right. But in general, there will always be more susceptibles than infectives. In general. Unless, you know, you're really pandemic or something like that. You know,
Right, I
you
guess
have
I-
100%, almost 100% infected.
So it's why, this makes me suspect that the threshold behavior of the vaccination comes from the artificiality that you don't have any susceptibles around you until people start getting vaccinated.
Right.
And,
Yeah, that's true for this example.
okay.
Yeah. Right. Yeah, so in some sense that's artificial. Okay. But if I do combine this rewiring with the vaccination, I can definitely use much less resource to control the problem, right? And eliminate the disease. So I can reduce my lifetime by quite a bit. Just by changing how often I randomly vaccinate as a function of time. Okay, so I want to analyze a mechanism as to what's going on here. Remember that in most of the cases, the extinct state is really unstable. So if I start near the extinct state, the natural dynamics will move away and go to the endemic state. So why does a disease go extinct at all? Okay, and so I want to backtrack and look at just a well-mixed population, no network, and tell you a little bit about some of the analysis in this very simple model, which is just an SIS problem here. So I just have susceptibles and effectives where the transition to infection is governed by a mass action term. Okay, and then kappa here is a recovery term, and I do allow birth and deaths in this particular model. So I've fixed my population size, and I assume n is large, and I'm going to constrain the population. And these are my parameters here. So I have birth and death rates that are equal. Again, another unrealistic problem, an assumption, but it leads to holding the population constant. And the contact rate of beta, which is the coefficient of the mass action term, and a recovery rate. And so I can define a reproductive rate of infection as this ratio of the number of contacts to roughly the recovery rate. Okay? Okay, and that's going to be my bifurcation point. And this is what it looks like if I plot the infectives versus this parameter R0, the reproductive rate of infection. When it's less than 1, I is, when the extinct state here, when I0 is stable. And for R naught bigger than 1, it's unstable. And I give rise to this endemic state. Similar to what I had before, but it's a much simpler model here. So this is used for a lot of different bacteria diseases, but what happens when I actually look at a stochastic run of this particular process? Okay, so I do some sort of Monte Carlo run. The noise actually comes just from the internal interactions of the individuals. And if I plot the time series of the infected as a function of time here, you can see that there's a lot of randomness in the fluctuations, right, which you kind of expect, okay, about some mean value that's predicted by the mean equations that I showed you before. And then at some time, you get the problem going extinct. But I told you before, the extinct state is unstable. Okay, this is for R0 bigger than 1. So the idea is the following. We can think of the endemic state as sort of lying at the bottom of some pseudo-potential. Okay? well. And so because of the randomness of just people interacting with each other, there's fluctuations here. And every once in a while, the fluctuations will be sufficient. It's much smaller than this height, but they'll organize so that you push up this hill to a disease-free state. That's the idea I want to get across. How does noise actually organize itself to do this so that you can overcome the instability of this, of the disease-free state? Okay, so the first thing is we can ask, well, what does the distribution look like of time series when you're either far away or close to that bifurcation point when r is equal to 1? So here's the infectives as a function of time. For something similar to what I showed before, you see a lot of randomness. But now suppose R0 is like 1.1. So here it's 2. And in blue, it's 1.1. Now it fluctuates, but then it goes extinct right away. And what happens is that there are two things. In the red case, when you're far away, you see the distribution looks almost stationary, where it almost is Gaussian around the endemic state, okay, of 100 here in this particular example. But when I'm very close to the bifurcation point, the distribution looks like this. So stuff is actually flowing to 0 much faster. And part of that is due to the size of the fluctuations. Remember, I told you, as you get closer to R0 equals 1, remember the size of the fluctuations has that nice scaling showing you how much larger they get. And as they get larger, it means stuff is flowing to 0 much faster. And that means also, in terms of this picture, that the fluctuations are almost comparable to this barrier here that you need to overcome. So what we want to look at are the harder problems when it's a rare event, where the fluctuations are much smaller than this barrier height. Okay, so we're far away from this particular point, r is 0 equal to 1. Okay, so we analyze this in the following way. Sorry if you don't know the math, but you can think of it as just notation for the moment. So I'm going to look at a master equation approach, where I'm going to define my variables in terms of this vector x, and I'm interested in knowing what the probability distribution, or the density is, of finding Si and R at some values. Okay? This is a very well-known technique, but I need to know also what the standard rates are of transitions of some increment, which I'll define as W. So each transition will have a rate. Okay? And I'm sorry about the screen. I didn't quite plan on 4 screens here. So the rate of change of the distribution is just the gain to the state x from those not in state x, which is given by the transition rate times the density, and take away the loss of those that are in the state, but now they are going to other states. Okay, so it's just a gain-loss equation for the distribution. That's it. Very standard stuff. You can look at it in a zillion books. I've just listed one here. And so what does that quasi-stationary distribution mean, right? So for quasi-stationary systems, I want the density to sort of behave like it's not changing in time, like that picture here I showed, right? This is a very nice-looking picture, far away from 0. Okay, and so when R0 is far away, I have another plot here of the probability where it's plotted as a function of the infectives here. X2 is now the infectives, and time here. And you see it's very, very steady. Whereas if I'm very close to 1, you see that I'm bleeding out here, right? So this density here is getting lower and spreading out, right? So these are supposed to be the initial one at 0, so you can see the difference between the two as time evolves. Okay, so I have a probability current that's flowing too fast here. So it's not quasi-stationary. And so we don't have much to talk about there. We're really interested in extinctions where this thing looks really stationary. That's the question. Now, remember I told you that the population depends on that the number of cases that we were looking at depended on almost an exponential function of n, the size of the population. So I'm going to make an assumption that the density actually scales like this, where the exponent is n times some function that's the state of the system. So I've normalized the variables here. Okay? And I'm going to call this S of Q just an action, like a mechanical system. Okay? And I get a Hamilton-Jacobi equation. And what's crucial is that I get this particular Hamiltonian. Okay? So I have these transition rates, which are now normalized to the size of the population, times this awful exponential here, where P is nothing more than just the, excuse me, the gradient of the action here. Okay? So this is very nice because I've taken a discrete system, I've turned it into something that was random into something that's going to be deterministic. Okay? That's just a technical detail. Okay, so what does it mean? Okay? Well, first, what I'm interested in doing is actually saying what are the dynamics of something. And that something is, I want to start at the endemic state in the mean field, and I want to go to this state. So I need to have boundary conditions for the states of infectives and their conjugate momenta. So to do it in some physically meaningful way means that, okay, we know at this point we're stationary, right? And so clearly the P is equal to 0 here. The conjugate momenta, this gradient term, is going to be 0. But over here, it may not be 0 because e to the minus ns is going to be approximately 0, okay, where n is large. So at the endemic state, I'm going to have p equals 0, but not necessarily at the extinct state. So what does that mean in terms of dynamics? So here's the dynamical systems part of the talk. I'm trying to describe the most optimal path that's going to go from the endemic state to the extinct state. And so I need equations of motion to do it. So I have a Hamiltonian. I can write down equations of motion, just like I would in a classical mechanics course. Okay? But I need those boundary conditions. Okay? So the nice thing about it is that, okay, I have, you know, my usual equations plus another set, right? So I've taken this deterministic picture of a random process, I've doubled it. That's the cost, and all my attractors go to saddles. You say, well, why is that? Well, if you think about the 1D process, I need an unstable direction somewhere. So if I have a 1D process, the only way I can escape topologically is if I introduce a new direction. Okay? So that gets me out of the attracting well that I showed earlier. Okay? And then there's a nice trajectory that's deterministic that will give me the most optimal path that connects the endemic state to the stochastic extinction state. Okay? And here's a picture of one. I'll tell you where this came from later. But the idea is that this is a prehistory of all those Monte Carlo simulations. I don't remember how many they did. Of all those simulations that went extinct. And this curve here is a picture of this particular path that we're going to call the optimal path to extinction, going from the extinct state down to the endemic state. And you can see that locally it lies along the local maximum, excuse me, of the prehistory, the PDF of the prehistory. That's what we mean by an optimal path here. It's still a rare event because we're in that exponential, right? Yeah.
So a number of slides back, you showed the red curve and the blue curve for the two different values of R.
That's right.
And the blue curve seemed to have much stronger, the bottom blue curve had much stronger autocorrelation. Is that captured in your Hamiltonian system?
Autocorrelation.
Yeah, so in other words, your red curve is just, going up and down. So if it was high at one time tick, it could be low at the next time tick. Whereas you could actually see a much, the blue curve, if a point was high, the next one would probably be high. So
yeah, it changes. It's
quote,
yes.
smoother.
So there is some correlation there that's due to the local dynamics. The frequency of the oscillations are changing as you get closer. Okay. So there is some. If you go to higher order terms in this expansion for the master equation, you'll get it.
Okay, so you don't see that till the higher order. I was wondering if that somehow was related to the derivative.
Right. Okay. All right, so I said all that. Okay, so that's how I'm defining the optimal path here. So it's still a rare event. So now I'm going to look at, the case where R0 is greater than 0 like we had before, but if I constrain the population so that I'm just making sure that there are no fluctuations in the total, right? And I recall this, I can write down the transitions for this 1D process, right? I can use this constraint to eliminate these susceptibles and just look at an effective population, okay? So this is what it looks like. So the transitions for the removal by recovery just means infectives are lost by 1. The infectives are also lost by death, and then this is my mass action term. So n minus x2 is like a susceptible population, okay? And so I can use all this in my Hamiltonian to generate equations of motion that I showed you the general framework of. Okay, so in blue are just nothing more than like a mean field. It is the mean field approximation, right? If I set P2 equal to 0 here, this is 1 and this is 1, and this vanishes here, and I'm just left with a simple one-dimensional dynamical system for the infectives without any force due to the conjugate momentum. So the conjugate, what I want to say is that this conjugate momentum term here actually is going to represent some sort of effective force of the noise on the system that's pushing me out of that well to overcome the instability. Okay. Keep that picture in your mind. And so when you look for equilibrium for this particular case, right, you have the disease-free equilibrium where both the infectives and the conjugate momentum are 0. There's an endemic state where you have the infectives which depend on 1 over R0 here, and P is equal to 0. But then the important one is you have an extinct state here where you have some non-zero boundary condition. That was what I was trying to get at before. And this actually is where the devil in the details are for any problem of this type, wherever you look at population dynamics, whether it's populations of epidemics, ecology, or chemistry, where you have finite numbers, and you're looking near 0, there's always something that depends on a non-zero conjugate momentum here. And what it looks like in this P2 x2 plane is the following. So here's my endemic state, okay? And along this curve, when P2 is equal to 0, it just behaves as if it was deterministic, just like a mean field. This would be the origin that's unstable, the 0, the extinct state. Okay, and so how does it get to this state if the stability comes along here? Well, that's provided by this non-zero boundary condition. So you have this nice curve here that actually you can find analytically in 1D. It's very easy. It's just a simple calculus problem. And then you can compute the line integral to find out what that exponent is. That gives us the shape of the distribution as a function of this parameter R0, the reproductive rate of infection. So this is the simplest problem and one can consider of this type. So it gives you everything you need, okay? And you get this nice analytic expression. You can actually compute everything here, and you even know what the prefactor is. So the extinction times, just think of it as proportional, inversely proportional to the density here. And so there's a prefactor we know. This is the action I just told you about, okay? And then there's a function of n here. And so you can plot what the extinction times are, or the lifetimes, as a function of R0, right? And so for R0 along here, we get great agreement, okay? Whereas down near R0 equal to 1, I start to diverge. And that's because the theory just doesn't hold there. The quasi-stationarity assumption fails, right? So you're in this regime right here. You start to see that. Okay. So that's that. You can actually put treatment in, okay? So if I'm infective, I can actually do some sort of Poisson treatment here, where I'm taking infectives and shoving them out back into some sort of susceptible class. And so I have all these transition rates here for birth, infection, and things like that. right? But now I've taken the treatment class, and I'm looking at susceptibles that are gaining and infectives that are losing at some average frequency nu. Okay, and that's how we made this picture. Okay, so here we were employing nu to be about 8 times per year. It's a moderate population of 12,000 people, and we made this PDF. Okay, so here's how many realizations. I don't remember. Did you do this?
No.
Who did that?
I
Leah did?
really-
Okay. Okay, and then the optimal path is this white curve. So you have to remember now in this full 2D case where you have both infectives and susceptibles, now where everything is fluctuating, I haven't constrained the population. This is a projection of a 4D plot onto this 2D surface because you've got 2 other conjugate variables each for infectives and susceptibles that you have to know in order to compute what this curve is. Okay. And then you can ask what the mean times to extinction are versus the theory. So here are the lifetimes, tau, and the Monte Carlo simulations are the circles. Okay, and the increase in frequency goes this way as a function of the amplitude of the fraction of people I'm vaccinating in the susceptible population. Okay, and so you see that you get this very nice decrease in the extinction times. By the way, these are actually units in years, and we're very close to R naught equal to 1 still here. But once you get down to here, your numbers get real, somewhat optimistic in the sense that your extinction times are very low. So there's an issue, with real numbers here. So I want to say something about resource management. Okay, so if we're doing something like, applying nu times per year of vaccine, where I'm applying it to a certain percentage, G, of the population that's susceptible, then I want to look at this as a constant and figure out what the best average strategy is going to be. So one way to do it is to constrain your total resource this way and plot the lifetimes versus G, and then also plot the lifetimes versus nu, always keeping G nu equal to constant. And you can see that, it's very easy to see that if I just look at increasing the fraction of susceptibles that are being vaccinated, I get a strict decrease, whereas not so with the average frequency that I'm applying it. So the idea here is that in this particular case where you have Poisson vaccination, that was a larger fraction treated fewer times per year is the most effective one. So this can give you, and again, the theory is given by the solid lines, the Monte Carlo are the symbols. And different resources here are available. Okay, so now I want to take all that machinery and now I want to move it into networks. Okay, so I'm going to extend the analysis to just stochastic networks, but I'm going to look at it first with no rewiring, since we're still working on the rewiring case. So now I'm going to ask what happens to the structure of a network on an SIS type of model like I showed before, where now my state space is the number of S and I nodes, but now I have SS links and SI links and etc. Okay? And I'm assuming that I'll have some average degree, as I did before at the beginning of the talk. And you can see what happens if I change a node here due to infection, right? So if I change this S to I due to, let's say, 1 infective, then the number of SI links changes and the number of II links change, right? So you get, they may not be small changes in the links, even though you change 1 node. And so it's very important to get the counting right for these guys. So in order to find the actual path in this high-dimensional space, we do a trick, okay? So we look along the network, sort of like this local idea, where we have so many connections, right? So let's say I have a degree of 20, okay, and I'm just interested in knowing what the dynamics of S to I along the local network are. But then at the same time, I know something I showed you before in the well-mixed population where I have a global situation, but I scale it in an artificial way. So I kind of know this. And then I want to also look at the recovery, right? Since it's an SIS model. Okay, and I just said that link numbers may be large, you know, when you have one node change, depending on the topology. So the reason I do this is that the optimal path is known numerically for the globally coupled case. Okay? And it turns out I can say something about how the nodes scale in this all-to-all connected graph, right? So the number of, let's say, SI links is proportional to the number of I nodes times the number of S nodes, for example. So I want to introduce a parameter that's going to be a constructive approach in order to find this path. So numerically, you're in this high-dimensional space. So I'm going to perturb this population going from the global coupled case to a finite degree case. Okay? So epsilon here is a homotopy parameter. When it's 0, it corresponds to no network structure. Whereas when it's epsilon is 1, it corresponds to local coupling. Okay? Something with finite degree. So I just said that. This is a rehash of my previous work, previous slides. And these are what the transition rates look like. So for local coupling, it's just going to be epsilon times the infection rate times the number of SI links. Okay? And when it's global, it's going to look like this. So it's going to be a mass action type of term. The number of S nodes times the number of I nodes. Okay, that'll be and then times something proportional that reflects the infection rate times this average degree. And the recovery rate is the same for both. I'm not going to go into this because it's just counting. But for the increments for each one of these, you know, you just have to count, you know, the number of S nodes, the number of the change, and the number of I nodes, etc. Right? So it's there are better people than I that can do this stuff. Okay, so what happens? So suppose I take a projection of this high-dimensional space, right? And I look at the fraction of I nodes versus the fraction of I links. Okay, so this is the globally coupled case, right? So where everything is all-to-all coupled. And then I turn this epsilon on, and I get this particular red curve for the finite degree network, right? Where I have an average degree of 20, let's say. Okay? And so the first thing you see is that, you know, I get a broader distribution of I links, you know, at the same number of nodes. You can compare this against the Monte Carlo when epsilon is equal to 1 in the full degree net, 20 network. Okay? So you can't see it too well here. It's actually pretty pixelated. But the white curve here is the theory, and the Monte Carlo is on this red stuff. And then over here, I've plotted the same thing, the fraction of I nodes versus the SI links. And I see very good agreement on both of these. So the theory matches really well. So what happens as a function of the population? So if I look at the log of the lifetime scaled by the population size, the Monte Carlo runs are in black here, and I do really well, right? The theory is right on. However, when I look at the infection probability here and plot the log of the lifetimes versus that, I have a general shape, but I'm off here by a little bit here. And the reason is that we know what the prefactor is in the globally coupled situation when epsilon is equal to 0. So, and we fix that at epsilon equals 0 right through, assuming that there shouldn't be much change in this prefactor. But it turns out that there obviously is some effect there, and it's showing up. So we understand this. And we could fix this curve by actually going through for each one and computing numerically what that prefactor would be. But we're honest, so we leave it. Okay, so then you can ask, well, now I'm going to turn on rewiring and just, for my final slide here, state what the steady states and the lifetimes are. So the lifetimes are these solid curves up here, the no rewiring case here, is in blue, and the small rewiring case is in red. And you can see that you get a big change in the lifetimes, and that they're reduced when you turn on very small rewiring here, which is, I mean, really small compared to what we were using before, 10 to the minus fifth on that order. So we're still working on the theory for some of these things. We have it, but we haven't finished it yet. So let me stop and entertain some discussion. I'll just reiterate that the big point here is that we were trying to extend some of these large fluctuation theories that we've been looking at for well-mixed populations to full-blown networks. And so we've been doing this now for random networks and extending it now to stochastic adaptive networks, where now human behavior is being taken into account in many of these situations. And by doing that, we've taken a stochastic system and put it in terms of a fully blown deterministic system that gives us this optimal path. And by doing the integral along that optimal path, we can predict extinction times. Okay, there's lots to do here. I mean, one can ask about different topologies. Okay, can you extend it to scale-free networks? Okay, that's a much harder problem because we're assuming a homogeneous network right now, on average. Okay, you can ask what happens if it's non-Markovian. Suppose there are delays in going from susceptibles to infectives or infectives to something else. Okay, that still has to be taken care of. We have a paper on generic bifurcations that just came out this year to describe that, but not to networks yet. Okay, and then suppose you have adaptation in a network, but you want to know what it is. Is there an inverse problem that tells you how to detect it? Can you do it? Okay, and there's just a zillion questions one can ask about this for multi-strain models, you know, improved control methods, what happens when you have external noise on this? Okay, and finally I'll close that we can actually do this in a higher dimensional setting for realistic measle parameters when you're really far away from R0 is 15. And so this is the optimal path. It actually spirals out here in this projected picture of a high dimensional case. And I think I will stop. You did that?
Yes.
Okay. And I'll take any questions, comments, discussions. Thank you.
You didn't say a lot about SIR until the very end. So how does SIR change does it change the basics of your conclusions? I mean,
no. I mean, you still get big changes. Oh, there are some papers you can see. I have some extra slides here. I think I have some. This is SIS. So here's SIR, okay, with vaccinations. So this is a little bit cruder, but the take-home package is the same, right? So you know you're plotting against the vaccination rate, okay, P here. And as you increase the frequency, you still get these big changes that are exponential. Okay? So you still see the stuff. The main problem is really when, once you get into here, right? So there's little contribution out here to the line integral, right? But once you get into here, it's where the major contributions are. Okay? And so that looks very similar to the SIS when you're near the extinction. You have to get out of the basin. And then overcoming the instability at the extinct state is the big problem. Right? That's where the biggest force needs to be applied. Any others? Yeah.
So have you thought about sort of heterogeneity in the network in the sense that some elements might correspond to children who are at the same kindergarten, whereas other elements might correspond to people who all happen to ride the subway together. So in different you can imagine sort of dividing your network into regions.
Yes. So there are various ways to do it for age structure, as you say, and also geographic structure. The models just become more complicated. The machinery is still the same. So we're looking at breaking the network right now. So, I mean, scale-free is sort of a hot topic. So this technique right now is difficult to apply in the scale-free way because writing down a density right now means you sort of compartmenting the degree distribution, right? But then how do you couple all those density equations? So that's an issue.
Yeah, at the boundaries between them.
Yeah, so trying to figure out how to do that. So now we're looking at breaking the network in a very simple way where you like have, we call it the mothership model, where you have very high degree nodes and then very low degree nodes, so separated by, let's say, a factor of 10. Okay? And that we can start to solve. And then the idea is to try to extend that to the scale free by busting up the various levels, you know, of the degree distributions in the scale-free case, where you have a fat tail, for example. Okay, so you use a lot of plateau functions or indicator functions to sort of bin that. But we've taken the very simple coarse case, right?
Right.
Just a two-step model, and so we have some results on that, but I'm not ready to report on it in this problem. Yeah.
So when you look at rewiring, you're conserving the degree distribution because you're allowing people that are connected to an infectious to connect to another person that is not infected, right? So, but would you consider the case where, the case of self-isolation, for instance, where rewiring doesn't happen all the time, and so the degree distribution of your network changes?
Yeah, so you can allow the degree distribution to change, but on average, you know, you still have to make some assumption as to what that mean value is going to be. You can also look at, for example, if you're rewiring, you know, an infectious individual, right? You know, usually the infectious individual is taken out of the population for a while, okay? Like he's sent home sick, right? And so people have looked at that, where, you know, you don't reconnect right away, right? But in those cases, then the network has a delay built into the rewiring, and that becomes non-Markov, right? There's some delay time there that's going to introduce a correlation. But you're right. I mean, you know, you could have time. I mean, I showed you the degree fluctuates quite a bit, right? But on average, it still hovers around 20, right? In that early picture I showed. So the degree is changing. You know, if you pick any node at random, you know, you see very heavy time dependence. Yeah.
Besides degree, can other network properties be considered, such say, related to the node centrality? It could be like closeness, betweenness.
Yes. Other people have looked at various kinds of things like that are just other measures of the network topology. Sure, closest and betweenness are just two of them. Others have looked at correlations, and you know, in terms of the nodes and the degree. We haven't done that here, but you can. But others have been doing that.
Yeah.
And also for an adapt. You know, so the other class of networks that is related to this are co-evolving networks. Okay, so and a lot of people have looked at those kinds of papers and looked at results for those kinds of network topology measures.
Questions? No more questions? Let's thank Ira again. Going to present you with this.
Oh, very nice.